Okay, so welcome back to another video. So here we have an indefinite integral from 0 to infinity of 1 divided by the square root of the square root of 5 to the power x. Add this with square root of 5 and then subtract 1 dx. So one might think it'd be impossible to integrate this, given with the little deceiving factor that we have a square root of some constant raised to a variable. But you shouldn't let stuff like that intimidate you because, we know as we learn in algebra that we know how to write, square roots in terms of exponents of fractions and then use that in terms of a bit of a simplification from there. And that's the idea on how to rewrite this integrand so it doesn't look as, scary looking or, intimidating. But the value of the answer actually does come down to a nice answer, and you'll see what that is. It just basically relies on, the whole thing is, of course, is calculus for one, but it's also, we're going to do a little bit of algebra manipulation, and then there actually requires a u substitution involved in this procedure. So with that, let's actually just jump right in. So as mentioned, just like I said, we can actually rewrite this, the square roots, the radicals, in terms of, the fractional exponents. So what we have is, now we have a new rewritten integrand of 1 divided by 5 to the power, so we have a 1/2 and then a 1/2, so that'll be 1 over 4, and multiply with the x, so we have 5 to the power x over 4, and then plus the square root of 5, and then subtract 1, then multiply with dx. It doesn't seem like we can do any much from here, right? Because there's no way we can actually use this, integrating techniques directly, or, look like to the point where we can actually integrate this in terms of some elementary functions. But again, that's why we have manipulation and rewriting for, certain like rational functions and integrands, of integrals. So what we can do here is we're actually going to multiply a 5 to the power negative x over 4 to both the numerator and denominator, and at least to some stipulation that will help that it will get rid of, the 5 to the x over 4, as if you multiply that, that's actually just going to give us back with just positive 1. And also, with this whole multiplication, this is still a constant on its own, so I'm actually just going to group that in terms of a parentheses. So with this, we have 0 to infinity of 5 to the negative x over 4, and then divided by 1. Then I'll separate this with, the parentheses, negative 1, and then multiply by 5 to the negative x over 4, and then dx. And so from here now, again, as mentioned, there's actually going to be a u substitution involved. So let's see. Let's actually suppose that we let u equals the denominator. So we have 1 plus the square root of 5 minus 1, then quantity, multiplied with the 5 to the negative x over 4. That if I take the derivative, then we know with a constant time raised to a variable, we know what the derivative, the standard derivative of that is. It's just the same thing, then times your ln of your base. Then you have to, don't forget to multiply your, multiplied with the derivative of your exponent. So performing all this out, we're going to have du is equal to negative, so the square root of 5 minus 1, then divided by 4. That comes from the derivative of negative x over 4, which is just negative 1 over 4, then ln of 5, and then multiply with 5 to the negative x, and then over 4 dx. So we have that, but it doesn't look like we can do exactly just yet, since there's still a dx that we want on its own. But actually we have a 5 to the negative x divided by 4, and then times dx. But this is actually nice, since as we see here, we have just that form. Then all we gotta do from here specifically is take this quantity and just divide that to both sides. And so that will just, it will just flip the reciprocal. So in other words, we have now a new substitution, a new form of du. So we have negative 4, then divided by the square root of 5 subtract 1, then times ln of 5, then du, then that's set to equal to 5 to the negative x over 4, then dx. And that's great, since now that'll just cancel out the numerator and this replaced with the new du differential that we have just, computed. So with this, let's actually just go back and then plug back that new substitution. And so now we have this new following. And don't forget that we also have to calculate our new bounds too. So we have the new bounds. If I plug infinity back into, for x over here, notice that 5 to negative infinity is just going to be 0. So it's 1 plus 0, so that'll be just 1 on the top. And if I plug 0, so 5 to the negative 0, that's just 1. Then 1 times this whole thing, so 1 plus square root of 5, then subtract 1, so we're just back with the square root of 5. 5. And so with this now, it's actually just plugging back the new du substitution, so -4. And I'm going to separate this out, so I'll have ln of 5, then put this in a form of a product of multiply by 1 divided by the square root of 5, then subtract 1 du, then all this being divided by u. Now let's actually fix this up a little bit and suppose that now I'll actually, not only will I switch the bounds and I'll just get rid of the negative because we have that square root of 5 supposed to be bigger than 1. So if I flip the bounds again, then I have the negatives cancel, and then I'll factor out 1 divided by ln of 5 outside, so that's still constant, so that's great. Then we have now 1 then to the square root of 5, and so that just leaves us with 4 divided by the square root of 5 subtract 1, and then divided by u, then multiply by du. Now, how do we actually tackle on this forward? It's actually not that as bad as you think, again, because, well, we have a simple calculation that we can actually simplify for 4 divided by the square root of 5 minus 1. As you can see that we can actually multiply the conjugates of both the numerator and denominator, and if actually just, if you simplify all this through, you actually get that this is actually going to equal double the golden ratio number. So now our new integral, our rewritten integrals, we have 1 divided by ln of 5, then multiply 1 to the square root of 5, then of 2 times the golden ratio, and then du, then divided by u. That's good since this is still a constant. I'll just put this outside. So 2 times ln, 2 times 5, then ln of 5, then with our same integral. Then this is just 1 over u du. We know that the antiderivative of that is actually just the natural log of u. So 2 phi and then ln of 5 multiply with ln of u, then evaluate this from the square root of 5 to 1. Obviously, we know that ln of 1 is just going to equal 0, so that's out of the question. So ln of square root of 5, again, if we actually just use our rules of natural logs, we can take that square root, convert that as a 1/2 exponent, then move that to the front of the ln. And so now we have that that's actually the ln of square root of 5 is just equal to just 1/2 of ln of 1/2 times ln of phi. So 5. I said 5, phi, excuse me, tongue twister. Then multiply with 1/2 ln of 5. Then we can actually see that this actually just cancels some stuffs out. ln of 5 will get rid of itself, and then the 2 and the 2 will get rid of itself. And then now we have that this is actually just the golden ratio number. So it's actually a special case of an integral over here that it actually comes down to a very nice number, just like that, / constant. So there you have it. So yeah, that's pretty cool if you ask me.